Thinking of a problem, an issue, a situation, or condition within the bounds of the built environment, we came up with Pollutile. This is a simple construction material to give answers to our chosen problem in the community condition, which is smog.
Heavy pollution, such as smoke fog, in major roadways in the Philippines harms the environment and the people every day.
According to Air Visual, Philippines has moderate pollution with PM 2.5 concentration. Philippines air is currently 1 times above WHO exposure recommendation.
And as of August 5, 2021, the Live AQI City Ranking ranks Quezon City as the most polluted city in the country, followed by Makati, Naga, Davao, and Batak, Ilocos respectively.
Our chosen material with potential for innovation is regular concrete. Concrete production is responsible for 8% of global greenhouse gas emissions, and as populations continue to grow, demand for concrete continues to rise.
In order to evaluate the environmental impact and resources used throughout the production and application of the material, here's the life cycle of a concrete, starting with the exploitation of the raw materials and ending it with the recycling or disposal of the demolished concrete. Basically, it addresses the environmental impacts of the concrete from the extraction and production of raw materials, and also the production phases of the concrete with the choice of the most suitable mixture for a particular strength and situations of use. The end-of-life scenario of CRC, or the completely recyclable concrete. All concrete waste is recycled within the cement production process, while for the traditional concrete, the waste scenario was divided according to 2 alternative routes, which include the recycling as concrete aggregate and the final disposal. So overall, the environmental impact of the concrete production process was found to be strongly related to its binder content and its required transport.
Knowing the properties and life cycle of our chosen material, we break down the problems into 3 points. First, product-wise, concrete is responsible for 8% of global greenhouse gas emissions, which is concerning nowadays, especially since the world is at high risk of global warming. As we evaluate the environmental impact and resources used throughout the process, we realized that the procedure in the life cycle of regular concrete could not be reused or repurposed again, which leads us to our last point. That regular concrete materials lack C2C or cradle-to-cradle cycle to reuse the concrete again and return it to the earth.
To answer these presented problems, we will give 3 keys that would be essential for a proposed innovation with regular concrete material. First, innovative materiality, which involves nanomaterial application, which in theory would play an important role. And second, by also integrating smart materiality like homeostatic facade. And lastly, third, in the wake of the digital revolution, we will apply Internet of Things, particularly air quality monitoring and testing using applications like Smart Air. Thus, Atelier A aims to innovate concrete into something new and useful for the country, especially in areas with high pollution risks, by creating a pollution-eating facade material that could instigate air pollutants, particularly in roadways, and contribute to significant improvement of air quality in the Philippines.
Introducing nanomaterials to Pollutile, we explore photocatalytic concrete with titanium dioxide. This is fabricated by adding the photocatalyzed titanium dioxide into conventional concrete. And this can help remove air pollutants, providing clean air in our cities and towns. Integrated with superfine titanium dioxide, which is a white permanent pigment, popularly used as a raw material in several downstream industries such as paints, paper, toothpaste, plastics, inks, and other products. Due to its whiteness, opacity, and refractive index, titanium dioxide is an important component in paints and holds about 25% share in the total content of paints. It is a chemical that can remove 88 to 97% of nitrogen oxide pollution from the atmosphere. Photocatalytic reaction can occur under the light when energy is higher than the photocatalyst bandgap. The form highly oxidizing hydroxyl radicals can react with contaminants and produce carbon dioxide, water, or other harmless substances. This material could be sourced in the market through importation of titanium dioxide from Wuhu-Loman Chemical Limited Company with an estimate of $2,010 to $2,850 per ton.
Applying smart materials to Pollutile, we incorporate the concept of homeostatic facade system. It is inspired by the compression of human muscles and homeostasis in biological systems. Homeostatic facade system regulates the building's climate by the process of self-shading. It has a silver layer that reflects light and also distributes electrical charge across the material, causing it to deform. This helps the facade to regulate temperature inside the building. Pollutile could be a component for an interactive wall collecting smog data on highly exposed surfaces. This could be locally sourced and made through companies like Sunframe Curtain Wall Engineering Corporation Limited, costing about $100 to $200 per square meter.
As we go on, we explore the potential opportunities with the Internet of Things. This is the interconnection via the Internet of computing devices embedded in everyday objects, enabling them to send and receive data. It is the process of sampling and testing of air emissions. It helps to understand the quality of air by pollutants and over a period of time. It also gives trends and patterns about air quality, whether it is improving or degrading.
Smart Air has been developed based on the IoT technology to efficiently monitor the air quality and transmit the data to a web server via LTE in real time. The device is composed of a microcontroller, pollutant detection sensors, and LTE modem. An application was developed to help in monitoring the air quality as well. Illustrating the process behind this, first we place sensor nodes in the Pollutile. Next, we collect data, in particular monitoring the quality of the air and pollutants present by programming using data management, model learning, and model verification. Third, after data collection with the only purpose of reducing health risks and raising awareness about the impacts of air pollution exposure, the data is sent to the IoT gateway cloud and processed towards the monitoring dashboard, which includes machine learning data analytics. This is then transferred to air quality monitoring applications for the right people to use this data to be studied to further combat and eventually mitigate air pollution in the country through Pollutile.
So in general, these are the processes applied to further develop our innovative solutions. First, we create a Pollutile clay mold. Then use titanium dioxide to make the photocatalytic concrete. In the final stages of the process, the concept of Internet of Things will be applied by embedding the sensors. Then expand Pollutile's application and effectively gather smog data for air quality monitoring and testing by using the homeostatic facade system. Pollutile's data would be sent to the cloud where it could be accessed using an application to effectively disseminate air sampling in the locations where tile is exposed.
We followed a basic component of the design for easier production by starting with a rectangular shape. Then we proceed to procure a triangular shape to create a strong and rigid form which resists deformation when external forces are applied. Structurally, triangles are sturdier than squares or rectangles. A triangle with hinges, even if loosely fixed, will retain its form. Their strength is derived entirely by their rigidity, until we derived our final shape tessellation.
These are the common dimensions for our Pollutile. It could be applied regularly like a tile or could be suspended through air to catch smog.
Now here's the proposed facade system, integrated with a combination of different responsive materials in order to address the problem within the built environment. The innovative facade is composed of the Pollutile itself, which is coated with titanium dioxide that has the ability to turn pollutants into water vapor and carbon dioxide when sunlight hits its chemically treated surface. Each tile was designed to contribute to its overall durability, design aesthetics, and sustainability. In addition to that, the facade not only addresses the environmental impacts of the pollutants, but also regulates the building's climate by applying the idea of homeostatic facade system, which responds to its environmental conditions.
This system is composed of double skin facades consisting of interior and exterior glass walls with a simple air cavity embedded with louvers. It includes mechanisms in response to the internal temperature of the building that enables the system to automatically regulate heat loss and gain while saving energy. Altogether, the proposed facade system allows the structure to blend with sustainability by integrating smart construction techniques while also translating innovative solutions to its form, having those triangular-shaped modules designed to maximize the surface area, control the building climate, and therefore increase the efficiency of this innovation.
When it comes into contact with smoke air, Pollutile surface will have reactants that would help create stable compounds in the air. This is made possible when the titanium dioxide is exposed to ultraviolet radiation from sunlight.
Further explaining this concept, as you can see in the diagram, when titanium dioxide is exposed to ultraviolet radiation from the sun, it absorbs radiation and electron excitation occurs. First, ultraviolet radiation is absorbed by the titanium dioxide, which causes the photolysis of water into superoxide ions and hydroxyl radicals. Second, nitrogen oxides react with the superoxide ions and the hydroxyl radicals to form nitrate ion. Third, the nitrate ions are absorbed into the block and form stable compounds.
TSM, produced by Heidelberg Cement in Germany, is currently the most popular titanium dioxide cement on the market. The procedure is similar to that of regular Portland cement, except that the titanium dioxide mixture is mixed in with other components in the final powder. Flexural strength, compressive strength, frost resistance, and absorbability were all tested on the TSM to ensure its integrity. The pressure applied in megapascal at the point of failure can be seen on the data collected in the first table. In the compressive strength test, the concrete block was placed vertically under a hydraulic press and pressure was applied on the failing point. After 2 days, TSM was able to withstand much higher pressure with an additional 1.1 megapascal in the flexural strength test and 11.8 megapascal in the compressive strength test. These tests show that adding titanium dioxide into concrete has no detrimental impact on its strength and that it still passes all standards. The sample was placed in a basin with a tiny amount of water with only one side surface of the block exposed for the absorption test. Over a period of a week, data was collected to see how much water was absorbed, and both the TSM and Portland cement samples had an absorbability of 8.1% in this test.
This shows the photocatalytic oxidation of nitrogen oxide under visible light on asphalt pavement surface, courtesy of ASCE library. For the sensors of Pollutile, we will place it in the middle of the tiles. For the proof of the concept and prototyping, we may use development boards such as Raspberry Pi, which could be bought locally with price ranging from 799 pesos to 8,000 pesos. For the final IoT solution, properly calibrated high-quality sensors and industrial IoT gateway devices, such as HMS Netbiter or equivalent equipment, are targeted.
Next, we plot down the cradle-to-cradle cycle for this product Pollutile. First, we start by creating a mold using recycled materials if we can. Then, we poured our photocatalytic concrete, and after this process, we start by coating it as well with titanium dioxide. By this step, it is ready for application to building facades, public areas, and mostly areas exposed to smoke pollution, together with the sensor nodes. After the recommended time duration for Pollutile, we proceed to dismantling, which leads into 2 ways in this cycle. The first part would be reformulated again into a Pollutile product, and the latter could be applied in landscaping to add texture for our landscapes.
Can be applied in major roadways in the country like EDSA, Commonwealth Avenue, and Makati. Next, it could add interest and adornment to smart building facades exposed in polluted air environments. And lastly, in public spaces where people could enjoy less polluted air through Pollutile. Here are some rendered illustrations of how the Pollutile would look like.
This is Pollutile's innovative processes and ideations in hopes of giving answers to the alarming effects of smog in our country through creating this building material with the help of modern technology as our advantage.